So we are going to take what we have looked at the last couple days and apply it to why it actually matters in regard to our model of the atom. Okay? So on Monday, what we did was we looked at the relationship between energy and frequency and wavelength. And we saw that as our frequency increased, so did our energy. So if our frequency went up, the energy of our wave also increased. And remember, if frequency is increasing, we have an inverse relationship between frequency and wavelength. So that means our wavelength would decrease. So the closer those waves are to one another, the higher the frequency, the more energy we have. On the flip side of that, we saw that if our frequency decreased, which meant our wavelength went up, okay, so those peaks got further apart from one another, we saw that our energy decreased. So the larger wavelength we have, the farther apart those peaks are, the less energy that wave is going to carry. So we can apply this to our visible spectrum. If we look at our violet, blue, green, yellow, orange, and red colored lights, we can see they occur with different wavelengths. So purple or violet is going to have the shortest wavelength, whereas red is where I have our highest wavelength. Since we know wavelength and energy are inversely related, violet is going to be our highest energy wave. Okay? Because the lower the wavelength, the closer those peaks are to one another, the more energy that wave is going to carry. On the other side of that, red, this guy has the highest wavelength, so those peaks are furthest apart. These guys are going to have the lowest energy. If you think about at a stoplight, when that light turns red, you stop, meaning that you have a very low or no energy. Perfect. We then looked to see how this applied to our different elements. So on Monday, we then did a virtual lab where we looked to see what color elements burned when they were placed into a fire. And we saw, depending on what type of element we had, they gave off different colors or different wavelengths of light. So for instance, we saw lithium burned red, whereas our potassium saw a nice violet color. What that tells us is that within our atom, we are going to have different amounts of energy or different energy levels because those elements are giving off different colors when they're heated. And we know different colors are associated with either higher or lower amounts of energy. So that would tell us that our lithium contains less energy than our potassium. Investigate how these findings impact what is occurring inside of our atom. So how can we use the flame test that we saw on Monday and apply that to what the inside of our atom looks like? So we are going to look at our new model of the atom called the Bohr model. So this is going to come right after Rutherford's model of the atom. And just like Rutherford, Bohr had a positive nucleus at the center of his atom. Okay. What Bohr did, though, is he sought to explain what exactly our electrons are doing and how the behavior of these electrons impact what colors we see when we heat up our different elements. So he said, our electrons exist on different energy levels, which are varying distances from us. Okay, so in our atom, we have our positive nucleus, and then surrounding it, we have different energy levels on which our electrons can exist on. And whether our electrons gain or release energy, we can move between these different energy levels. Okay? And depending on how much energy we gain or release, tell us what energy levels we're able to move between. This is going to be what we investigate today. That is found in your personal homework folder in one. Okay. To find the simulation itself, we are just going to Google Bohr model of atom McGraw-Hill. Okay. And it's going to be the first link that pops up. You may need to enable Adobe Flash Player either by clicking at the center here, or you'll see a little pop-up over here on the right-hand side of that URL that you'll need to click on that will allow you to enable Adobe Flash. And once you allow Adobe Flash, you should see this screen. So we see our positive nucleus at the center of our atom and these different energy levels at different distances from the nucleus. Okay. So what our electron can do is it can move between these different energy levels. So right now I'm on orbit 1. This is going to be what we call the ground state. That is the level that's closest to our nucleus. If I want to move to the second energy level, we see a couple things happen. Okay? We can see that on the second energy level, that electron is moving faster. So that tells us it gained energy. Okay? So it needed to gain energy in moving from that first to second energy level. If you guys noticed, there was a little purple arrow that came in and hit that electron in order for it to move. That is going to be what we call a photon. And a photon is going to be a particle of light that can transmit energy. So that purple photon came in, gave our electron enough energy to move to that second energy level. Okay? And it'll tell us what wavelength of light our electron needed to absorb in order to make that move. If we think back to that video that we watched on Monday, we could then use this wavelength to figure out just how much energy that electron needed to absorb in order to move from the first to the second energy level. In moving to that first to second energy level, we also notice something over here on our absorption spectrum. So we can see in this example, we needed to absorb a photon of purple light with a short wavelength, so a high energy in order to make that move. So this absorption spectrum tells us what type of light or what type of photon we needed to absorb, how much energy we needed to gain in order to move to higher energy level. If we move back down to the first, we can see in that example, a purple photon was given off. So in moving from the second to the first energy level, our electron releases energy in the form of purple light. And we can, again, see what energy was released by using the wavelength of the photon that was emitted. So in moving from a higher to lower energy level, we're releasing energy in the form of colored light. And we can see what kind of color light we are releasing in this emission spectrum. So in our emission spectrum, that'll tell us what type of light or what energy wave we needed to release or emit in moving from a higher energy level to a lower energy level. Okay. So in the simulation on the first page, you're just going to kind of play around, see what needs to happen in order to move to a higher energy level, what needs to happen in order to move to a lower energy level, and so on. On the second and third pages, you're going to be making very specific jumps, and you'll want to pay attention to the type of wave or the wavelength that is emitted or absorbed to tell you how much energy was needed in order to make that transition. If you guys have any questions, please do not hesitate to let me know. On Friday when we are never mind. Well, I'll see you guys on Thursday. I hope you guys have a great day. Let me know if you have any questions.